What is up, Algebra 1? We are on the home stretch. We just have 3 examples left to do. Example number 5. This time, instead of giving the values in numbers, we are given a graph that we need to analyze important parts of. Very, very popular OST. Example 5, the following graph shows the relationship between the amount of materials, which we can see right here going up and down, the amount of materials in grams that are available for a critical life-saving drug. So we got amount of material and we have time. Okay, so first question, what is the initial value? Where is this located on the graph? The start of our graph begins at time 0. So if I follow my y all the way up, my initial amount is right here at 360. So my initial amount is 360 grams. And where is this located on the graph? Well, this is my x-axis, this is my y-axis, and this point is on the y-axis. So this is the y-intercept. Part 2. Is this a growth or decay function? Okay, this problem is going down over time. Since our graph is going down as time goes by, 0 years, 2 years, 4 years, 6 years, we're going down. That means that this is a decay function. Okay, this function is decay. What does this mean for the life-saving drug? That means that as time goes on, the amount of material is also going down. Okay, take a second, pause the video, and try example number 5. Example number, 6. Alright, you've taken some time. The following graph shows the value of a laptop after you purchase it. Okay, what is the initial value and where is it located? Just like the problem you just did, here is my start at time 0. The value of the laptop is $1,800. Okay, where is it located? Well, of course, this is the y-intercept. Okay, your initial value is always at the y-intercept, the start at time equals 0. Is this growth or decay? Okay, in this problem, it is a decay function because as time goes on, the value of the laptop is decreasing, going down, decaying. Would it be possible for the value of the laptop to increase over time? What would that mean? Okay, would it be possible in this scenario? No. No, it is not possible in this scenario for it to increase. Okay, as we use an object, its value is lost. However, maybe it becomes collectible over time and something where it would to happen. In order for it to increase over time, it would have to be an exponential growth problem. Okay, so let's name a scenario in life where the value of an item goes up after purchase, where an item goes up after purchase. Okay, so one excellent example of this might be something like a Pokemon card that's highly collectible, like the first gen Charizard. Bad boy's worth near $1 million now. Okay, collectible cars go up in value over time. Stocks can increase in value over time. Okay, there are many scenarios in life where purchasing an item, it does go up over time. Another one that happens a lot are homes, houses. They can fluctuate up and down, but that is something that can go up in value over time. Okay, we just got one left to do. Most important problem of our lesson. Example 7. The population in hundreds of koalas at a nature preserve T years since the beginning of 2011 can be modeled by the expression. So let's first just write this down. Here's our exponential expression. 1.98 times 1.11 to the power of t. And there's a couple things we have to remember. First off, this is the population in hundreds, okay? So whatever number we see, we need to multiply it by 100 to get the actual number, okay? We know t is the number of years since 2011. And that's all that the problem tells us. Now, we can get a lot from here. So first, the problem is asking, the populations of koalas at the beginning of 2011 was blank. Okay? Keyword here is the word beginning. Okay? What was the start? And we know our growth formula is A times 1 plus R to the power of t. A is the start, okay, the initial amount. So our initial amount is right here, but here's where we have to be really careful. It's not just 1.98, okay? We can't write that because this is the population in hundreds. So 1.98 we have to multiply by 100, okay? We have to multiply this by 100. When we multiply it by 100, we get 198 koalas. Next part. They're growing at a rate of blank every year. Okay, R is right here in our exponential growth formula. So this entire number is not the growth. This represents 1 plus R. Okay? So if we have 1, what would we have to add to it in order to get to 1.11? Well, we would have to add 1 plus 0.11 or 0.11. This is our growing rate. Remember, we want to write it as a percentage. So we're going to take 0.11 and multiply it by 100 to get 11%. 11% every year. Okay, and that's exponential growth and decay. Congratulations, bye.